Good evening, everyone. I would like to welcome you again to today's class. Today is the fourth facilitation in Chemistry 203 class. Ahead of time, I've sent you the video for this class, which contains the instructional material. So after that, we're going to be looking at any of the area of concerns that any student might have. So you can signify it by raising up your hand when we start the class. So you ask your question, we can look at it together. And if there's no question, then I may have some questions so that we can have a look at such together. My name still remains Professor Lainka Jani, your facilitator for CHM203. Welcome, and remain blessed as we stay tuned to complete and to continue this journey together. Thank you. Is there anyone that have any question before we look at some questions together? If there's anyone, please, that have questions from the video that I've sent earlier to watch before this class, please let's signify by raising our electronic hand. Then I'll give you the audience by calling you up to ask your question. If there's no questions, then I want to believe that all the content of the video you watched was well understood and there is no challenge. So we can just look at something briefly from my side here. Any question? Buhari Musa. Any question?
And not really.
Okay, thank you very much. Can you see the slide?
Yes.
Okay, so let's look at the slide briefly. It's since nobody has question. Thank you very much. Okay, in this topic number 4, we're looking at the module 2, unit 1 under the functional group and reactivity in organic chemistry. And we are looking specifically at arcane, free radical substitution reaction in arcane, and the reactivity and selectivity principle. Now, when we're talking about the physical property of alkanes, these are the properties that can be used to identify alkanes. And we say when we look at alkanes that are called aliphatic alkanes, straight chain alkanes, that are normal without any branching, we'll discover that careful looking at them from one to another, we'll discover that there are some peculiar trends that we can use to predict some things about them. So as the number of carbon atom increases, each additional methylene group contributes a fairly constant increment to some specific physical property, especially the boiling point, the melting point, and the density. Of course, we know that boiling point is the temperature at which liquid turns to vapor, while melting point is the temperature at which solid turns to liquid. So it makes it possible to estimate the property of an unknown member of a series from those of its neighbor by that chronological similarity in their trend. Like, for example, when we look at the hexane, which is 66814, and its next immediate neighbor, heptane, which is 67H16, we discover that the boiling point of the two of them is 69 and 98 degrees respectively. And when you look at it carefully, it's as if you have added a CH2 to hexane when you are getting the heptane. Now, for that CH2 unit that was added to the next neighbor, we discover that it's predictive enough that, okay, if you look at 69 degrees centigrade to 98 degrees centigrade, we see a roughly 28, 29 degree difference between the two. And that makes us to say when you go through the trend of the normal arcane, not the branched one, you can use this to predict even their boiling point before you get to the experimental determination. So if you have hexane being 69 and you have heptane being 98, then we are saying if we keep adding constant of 29 degrees, we can predict the boiling point of the next after heptane. Of course, you know hexane is 6 carbon, heptane is 7 carbon, octane is 8 carbon. So if heptane is 98 degrees centigrade, then if you add that 29 degree centigrade to it, it's going to give us 127. And that's why we are saying we can predictively say that the boiling point of octane is 127 based on the trending between that of hexane and heptane. So if we truly want to confirm this, we need to look at the experimentally determined value for this compound. And this is the table of experimentally determined physical parameter for that for those straight chain alkane. If you look at hexane now, you have hexane at 68.7. Of course, if you try to do that approximately, that will be 69. And if you look at heptane, it's 98.4, and that's approximately 98 degrees centigrade. So when you look at that 69 degree, when you had a constant of 29 to it, you get 98. And that's exactly what you have for heptane. We are saying that if you had 29 degree to 98, it's supposed to give you roughly the boiling point of octane, which is the next neighbor. And of course, when you look at it very well, you see 98 plus 29 is 127. And of course, when you look at octane, it has boiling point of 126, which means that a plus or minus 1 degree, this prediction is accurate. So we see as CH2 is added to each of the alkane and the chain is becoming longer, then the boiling point at the melting point is increasing at a particular similar trend. And we look at that of octane to that of nonane, you discover that from 126 now, if we add that same constant to it, you are going to be landing at around 152, 151, which is exactly what we have here. So we are saying that there are physical properties that can help you to identify alkane, and this physical property, they have the way they vary. If you look at density of the, you know, density's formula is mass per unit volume or mass over volume. So the heavier the mass of a compound, of course, the higher the density will become. When you look at the density of propane that has 3 carbon, is 0.5. And when you look at the density of octane that has 8 carbon, is 0.7. So you can see the density is increasing as the mass unit is increasing. So for every CH2 or methylene increase, there's always a unique addition in the density. Of course, there are 5 characteristics of homologous series, and we can use that to compare with, say, the branch chain isomer. The trend that we observe in the straight chain isomer are not obeyed when you come to the branch chain isomer. So the higher the degree of branching, the lower will be the melting and the boiling point. This is the reason why octane could not be a good fuel to be used as petrol, but its isomer, which is having 3 degrees of branching, which is 2,2,4 trimethyl pentane, is a better petrol to serve as fuel. So I'll ask us some questions. This is a graph of the boiling point of alkane. And when you look at the alkane, you discover that the N-alkane, which you have the color up there, has higher, you can see it has higher boiling points than the branch chain isomer. When you look at this, wherein it's a straight chain with n being number of methylene group inside. Now, when you have this one with n number of methylene group, but with a degree of branching, you discover that the boiling point lowers to this place. So the higher the degree of branching, because of this isopropyl group alone, whatsoever happen here that make this place to be similar to this place does not obey the rule anymore. So this one is a straight chain. Therefore, it will have a higher boiling point. This place is a branching, therefore, the boiling point lowers, which is the reason why we have what we have in this graph. Chemical reactions of alkane, which you have understanding that alkane under normal condition and have no or little affinity. That's the reason why we call them paraffin. And that paraffin comes from two Latin words, which is parum and affinium. Affinis and parum means little affinity. So most of the oxidizing and reducing agents, they have tremendous power to transform alkene and alkyne. When it comes to alkane, there's no show, because alkane is an sp3 hybridized carbon throughout with single bond which has sigma bond throughout, stronger than a pi bond, so they could not accommodate anything coming in. The only set of reaction that they are permitted to undergo is halogenation in the presence of high photon energy, or in the presence of peroxide, or in the presence of UV light. So ethane is not reactive to hydrogen gas in the presence of catalyst. Alkane undergo complete combustion with oxygen at elevated temperature. Alkane, of course, hydrocarbon, they burn in oxygen to give carbon dioxide and water. And another thing we need to know about them is that the lower member of these alkanes are gases in nature. And that gas is the first three, apart from the first four, which is the first one and the three. And what we are saying is that methane, ethane, propane, and butane, they are the component of what is called natural gas. And it might interest you to know that Nigerian source of crude oil bed has more of natural gas. And when we're talking about natural gas is a mixture of 75% of methane plus 25% of the other three, ethane, propane, and butane. Of course, that's ethane, propane, and butane form majority of what we call liquefied petroleum gas, which is what we use in cooking. So the natural gas is that component. So petroleum is a complex mixture of alkane, cycloalkane, which exists in solid, liquid, and gaseous form. And of course, it is interesting that they can be separated into their various fractions using a more advanced distillation with a fractionating chamber. And that's why we call it fractional distillation. So petroleum, of course, is the same thing as crude oil, not the same thing as petrol. Petrol is just one fraction out of plenty of the mixture of fractions that made up the petroleum. So you can see the combination and what it results into. If you have between carbon 3 and carbon 4, that's propane and butane mixed together will form the liquefied petroleum gas, which is what we use in cooking. The first class activity. If you drop a lighted matches on some petrol or gasoline, it ignites almost explosively. Of course, the petrol is a component of crude oil or component of petroleum. If you drop a lighted matches on tar road, almost certainly nothing will happen. Why? Can somebody help us? Can somebody attempt that question? Yes, Buhari Musa.
Okay. Since the third road is solid.
You know that the tar road is also made from the product of crude oil, right?
Yes, I know, which is
And
asphalt.
good, very good. And petrol is also a product of crude oil. Why is it
Yeah.
that when you light the matches of petrol, it ignites explosively immediately, and you light the same thing on the tar road, nothing happens?
The third road is already dried up because there are no fumes, and it's mixed with tarmac, which is cement, gravel, and others.
Good, good.
Though the tar is it depends on the forms. If it is on the gaseous state, the fumes is flammable,
Ah,
but the solid one is not flammable.
very good. So we know that the higher the number of carbon atom, the less reactive with fire it will be. Of course, we know that petrol is liquid, is a low liquid, and then it can easily get the challenge. It can easily be ignited with the fire. But if you are looking at tar is solid part of that component, which of course, it has low affinity for light and for fire. So when you have that, you know that it will not ignite like the way petrol will ignite. Petrol is liquid, and petrol, of course, will ignite more than some other liquid. Why? Because petrol is highly volatile, it's highly flammable. So when you're even talking between liquid, comparing how they can catch fire, it will still vary. The way petrol will catch fire will be higher and faster than the way diesel or kerosene will catch fire, even though they are all liquid. So if we are now considering petrol with tar, which is the solid hydrocarbon, then you can see that the higher their key chain length, the lower will be their combustive nature and power. So number two, liquefied petroleum gas is mainly composed of what? Can somebody help us apart from Buhari?
Listen.
Oguta, yes.
Yes, I think LPG composed of propane and butane.
Very good. LPG contains propane and butane. What's the major usefulness of that in man?
Well, they are used as fuel for cooking.
Yes, every fuel that you go to filling station to fill your cylinder for your cooking, that's what they fill there in for you.
Thank you, sir.
What is the difference between LPG and natural gas?
I think natural gas is a combination of methane, 75%, while and 25% of a combination of methane, propane, and butane.
Which one is
and
that?
The natural gas
Is what?
is a combination of methane, 75% methane, then 25% of ethane, propane, and butane.
Very good.
Natural gas.
Okay, thank you very much.
You're welcome, sir.
Can I attempt?
No, somebody has already given the answer.
Okay.
And it's correct. So the next question, you may likely want to
Right.
try to attempt the next question. Now, when we are talking about alkane undergoing combustion reaction in the presence of carbon, in the presence of oxygen to form carbon dioxide and water. If you look at this equation very well, there's something that comes to mind. And what comes to mind is that you must know how to balance the chemical equation in order to establish some facts. Let me give you a question from here. If somebody can help us to attempt a question. If pentane undergoes complete combustion in oxygen, how many mole of carbon dioxide and water will be produced? If pentane undergoes complete combustion in oxygen, how many mole of carbon dioxide and how many mole of water will be produced. Of course, we know that pentane is an alkane. Pentane means spent, it has 5 carbon, and because it's in, it will have 12 hydrogen, complete saturation. So we are saying C5H12 undergo reaction with O2 in excess. What will be the amount in mole of carbon dioxide that will be formed and the amount in mole of water that will be produced? Can somebody help us?
Hello, sir.
Yes.
I think we have 5 mole of carbon dioxide and 6 mole of water.
Very good. So if we look at that, there's a trend that can help you to predict anything without you even trying to struggle for anything. What do I mean by this? If you look at the monotonous trending that you have here, you discover that the total number of your carbon in your hydrocarbon starting material will be exactly the number of mole of carbon dioxide, because it means all the carbon in your starting material is completely converted to CO2. So if I ask you complete combustion of pentane, and pentane has 5 carbon, you will know that there will be 5 mole of carbon dioxide. And of course, the interesting thing is that when you are able to do it well, your water will always be +1, the amount in mole of your CO2. If you have 5 CO2, you have 6 water. If you have 10 CO2, you have 11 water. If you have 20 CO2, you have 21 water. So that I want you to get here. Instead of cracking your brain and thinking and up and down, how do I do this? How will I not do this? Then when you are able to get this trending, then there will not be any challenge. See, for example, heptadecane, that last equation, heptadecane, complete combustion of heptadecane in oxygen. Heptadecane, of course, you remember that decane means 10, hepta means 7. So if you say heptadecane, that's 7 plus 10, that's 17. If you have 17 carbon and you say it's an alkane, of course, you know that hydrogen must be double of the carbon plus extra 2. So if they say heptadecane, it will be 617H36. So if that reacts with oxygen, of course, it's going to give you total number of carbon there is 17. So it's going to give you 17 molecules of carbon dioxide. And you see that the number of hydrogen there is 36. If you divide that 6 by 2, that's 18. So 18 to 2 places will give you 18 H2O. So that's 17 plus 18. Let me ask this question. Heptane undergoes complete combustion to form X molecule of carbon dioxide and Y molecule of water. Solve this equation, X plus Y minus 2. Can somebody help us to attempt that? You have to solve that equation.
Please, the question again.
We said heptane undergo complete combustion in oxygen to form X molecule of carbon dioxide and Y molecule of water. And I say solve this equation. X plus Y, solve this equation, X plus Y minus 2. What would that be?
That should be.
So it means before you can solve this equation, you must first of all identify what is X, what is Y, then you can impute them in that formula to get your answer. Okay?
Yeah. Yes.
Who wants to help us? Who wants to help us?
Hello, sir.
Okay, Buhari, your hand is up. Yes.
That should be 7 molecules of CO2 and 8 molecules of water.
That's 7 molecules of CO2, that 8 molecules of water. Very good. Yes. But is that the question I asked?
Now we are looking for X and Y.
We already know X plus Y now. You already know X and Y now. But the question is now is that solve or find the value of X plus Y minus 2.
Okay, find X plus Y minus 2. That is 13.
Very good. So once you know that equation and you compare them, you know X, okay, you have heptane, that will be 7 molecules of carbon dioxide plus 8 molecules of water. So X is 7, Y is 8. So just say 7 plus 8 minus 2. Then that now is my final answer. So thank you very much. Let's try and look again at some other. Of course, this place should not have any problem again. So if you have to balance equation, you see that all those ones that I gave you, the odd number of carbon, therefore they have straight away molecule. But those ones that are even number may have fraction. So anytime there is fraction, there is no big deal. You can now use 2 under this 9 is 2. You can use 2 to multiply all through. Then you get 2 molecules of butane. We react with 9 molecules of oxygen to give 8 molecules of carbon monoxide and 10 molecules of water. That is when we are talking about incomplete combustion. Always note the difference between the two. Incomplete combustion is it produces carbon monoxide. That's what happens when the engine of a car is going away. When the engine of the car is about to completely stop working, it will be working under pressure. And then when it's doing that, you discover that the fuel will not be able to combust completely in oxygen to form carbon dioxide and water. Then the engine exhaust will begin, the car exhaust will begin to bring smoke. That's carbon monoxide. So that's telling us that the oxygen could not be completely combusted on your fuel through, which is your hydrocarbon anymore. And that's why we say, oh, you need to ring the engine or you need to change the engine. So you must know that this is carbon monoxide under unlimited supply of oxygen, but it will be carbon dioxide under the excess supply of oxygen. Of course, here we say the free radical reaction are divided into 3. We have the chain initiation, we have the chain propagation, and we have the chain termination. Of course, when you look at such, you discover that alkane normally will not undergo addition reaction. However, in the presence of UV light or peroxide, free radical could be produced. Free radicals are hot electron species that are very reactive. Because of that one electron they have, they are very unstable. Therefore, they are willing to go up and down to attack anything attackable, to form anything formable. So when you look at chlorine gas as Cl2, it's non-reactive. If you have to react that one with methane, there will not be any reaction. However, by the time you bring the light in, what will happen is that the chlorine gas will split into 2 chlorine atoms, wherein there's one odd electron. It's no longer lone pair, pair. It's no longer a pair of electron anymore. So when you do that, you see there's an odd electron here, only one. That makes this chlorine to be very reactive. So instead of Cl2 now, you now have Cl with one odd electron and Cl with one odd electron. So this odd electron Cl is a Cl molecule that breaks into that. That's why we said it has initiated the reaction here. That's why we call it chain initiation step. Now, when a free radical now see a neutral alkane molecule, it will cause the problem to occur. It will replace the hydrogen, and the second chlorine will pick the hydrogen that is replaced. So you have HCl, and you have your free radical. So this free radical of methyl group can now continually attack to have order. So when a free radical attack a neutral molecule, it will produce another free radical and a neutral molecule. When the free radical is present in any vessel, it will keep attacking neutral molecule to keep producing new molecule and new radical. But immediately two radicals, so that one is called chain propagation. It can go on as long as your product is still having at least one radical. That radical will attack a neutral molecule. It will cause reaction to produce another thing. If that wants to generate a neutral, a free radical, it will keep attacking. However, if two free radicals now meet each other on the way, then that will be the end of it, because they will now form a ribbon. A free radical of methyl group, a free radical of chlorine. By the time they come together, the chain will terminate, and you have a neutral molecule without nothing to attack it anymore. Then that reaction stops there. And that's why we call that third stage chain termination step. Chain termination step. And in this one, to form the free radical, reaction always produced by homolytic cleavage. Homolytic cleavage has to do with two atoms are joined together with one bond in between them. Or of course, that one bond between them is equivalent bond, because one electron each is what they donated. If A collects his one electron back and B collects his one electron back, so what we will have at the end of the day is A radical and B radical. So we are saying homolytic cleavage will result in radical formation, which is the mechanism technique through which electrophilic substitution happens in alkane. Heterolytic cleavage is not right, because in heterolytic cleavage, you have ion formation. That one is not necessary, and it will not be the mechanism for preparation of free radical substitution in alkane. Because the one that picked the two electrons will be positive, the one that picked nothing will be, the one that picked the two electrons will be negative, and the one that releases one will be positive. So it will form cation and anion. I know there's no problem with all this side. The rate of reaction was well explained in the video. The distribution and how to predict the secondary, the minor product, and the major product for compound. If you are trying to do chlorination, it is easier to do chlorination of methane because you have only one carbon. It is easier to do chlorination of ethane because you have two carbon, either carbon 1 or 2, any of them can be equally attacked. However, when you begin to have more than 2 carbon, then there may be preference. There may be preference. Like for example, when you are looking at methane, propane. Propane is CH3, CH2. If you are trying to do chlorination of propane, you see that you begin to have more than one chances and more than one choices. So when you know that, you must know how to predict well. When you want to do monochlorination of this, by one chlorine out of this coming to replace hydrogen. Of course, there are two tendencies here. One hydrogen from the methyl group can be removed for chlorine to come in, or one hydrogen from methylene group can be removed for chlorine to come in. When you are trying to chlorinate the methyl group, you have 6 chances, because from this first methyl, this is also a methyl group. There are 6 hydrogen. Each one of them have equal chances to be replaced by that one chlorine that wants to come in. So if you have to form a primary chloride product, you have 6 chances. But if that chlorine wants to come to the secondary group here, you have only 2 chances. And of course, when you look at that, when it comes to this middle one, it's coming to a secondary carbon. When it comes to this number 1 or number 3, it's coming to primary carbon. Therefore, the 6 chances, we have much more products replicate from itself than the 2 chances. So that will tell you that if you do this under non-normal condition, 1 chloropropane will be a major product over 2 chloropropane because of the number of chances. Of course, when we are talking about this one that you are using butane, instead of 3 carbon, you want to use 4 carbon. And you need to chlorinate with 1 out of this chlorine alone. So when you look at that, you know there are 2 chances. If you put it here on chlorine number 2, on carbon number 2, or you put it on this carbon number 3, they are equal chances because both of them are methylene. If you put it on carbon number 1, there are 3 hydrogen that have equal chances of being replaced. Or if you put it on carbon number 4, there are 3 chlorine that have equal chances of being replaced. So when you look at it, this is a chance. Whether you are chlorinating carbon 1 or carbon 4, it will still give you the same thing. So we are saying these chances is having 6 hydrogen that can be replaced by that 1 chlorine. And this middle one have 4 chances of hydrogen that can be replaced with that chlorine. So when we look at this now, like for example, if chlorination, we have to come on carbon 1, there are 6 chances because 1 and this last have equal chances. If that chlorine have to come to this position 2, there are 4 chances because each of these carbon carry 2 hydrogen that have equal chances of being replaced. So it is possible for you to have 1 chlorobutane or to have 2 chlorobutane. So, but what will be the chances there? We discovered that when we did the expected thing is that you have 60% of 1 chloro and you have 40% of 2 chloro. However, in the experimental, we are having 29 to 71. What could have allowed this to happen? It's because this is formed as a form of radical. So if you are trying to substitute at position 1, it means when it loses 1 hydrogen in position 1, it has a radical that is a primary radical. And of course, when you have a radical, it's different from when you have a ion. So we are saying that when you look at this, the tertiary radical is much more stable than the secondary, and the secondary is much more stable than the primary. And therefore, when you look at that, you discover that when you have this primary radical, you see that it is less stable than the secondary, and secondary is less stable than the tertiary. This is the reason why expectation according to the theory, this one should have been the major product, and this should be the minor product. But when the experiment was conducted, the reverse is the case. This one is now the smaller, and this one is the major. So which help us to know that a tertiary truly radical is much more stable than the secondary. You know, the secondary is a carbon that linked to 2 other carbons. And the primary is carbon that linked to not more than 1 other carbon. So we are saying that this is greater than this is greater than this, and that's the reason why your primary now having lower yield in the experimental determination. So the expected statistically distribution of the product is supposed to be 60 for 1 product and 40 for 2 chloro product. But experimentally, that's not what was seen. Then in order to explain that, we now discover that, oh, the alkyl radical stability has a long way to predict what will be the experimental yield of things. So if tertiary alkyl group is much more stable than the secondary, and secondary is much more stable than the primary, then you know that secondary will have gained more ground than the primary in small time. So when my primary is still trying to make its way, secondary has already started because of its stability, and that's what gives us this explanation for that. So stability of alkyl radical is a key factor showing the reactivity. So when you're talking about reactivity, you must put that into consideration. So it is easier to form secondary alkyl radical than primary. Hence, 2-chlorobutane is formed faster than 1-chlorobutane. At room temperature, it's 5 times easier for a chlorine radical to abstract hydrogen from tertiary than from primary, of course. And it is 3.8 times easier to abstract hydrogen from secondary than primary. This is the reason why you have secondary having a higher yield than the primary, and the tertiary having a higher yield than the secondary. So if you watch the video, everything is already in the video. How to calculate this reactivity, everything I explained it in that video, which now justify why we now have 29% for 1 chloro product, and we now have 71% experimentally for 2 chloro product. The reason is that making use of the relative amount of what you have there, the probability and reactivity must be used to get the reaction rate. You see the probability and the reactivity. But that expected one that we said the other time was using only one factor. That was the reason why it's having 60 and 40, which is not correct. But experimentally, we now discover that much more than reactivity, there's probability. So probability and reactivity are 2 major things you must factor together in order to get the right justification for your yield, which is what we are trying to explain. Why do we have 29 of 1 chloro and 71 of 2 chloro? So if you do that, you discover that if you want to use the rate, you discover that there are 6 chances for the 1 chloro product. You remember 3 methyl group in 1 and 3 methyl group in number 4. So 6 chances, and we know the rate of reaction in terms of the probability is that the primary is, if it is 1, then the secondary will be 3.8 faster, and the tertiary will be 5 faster than primary. So if you look at that, the number of hydrogen multiplied by the reactivity. So if you look at this 1 chlorobutane, it is a primary. Therefore, the reactivity ratio will be 1.0. And there are 6 hydrogen that have equal chances, the first methyl and the last methyl. So if you multiply that, you get 6.0. Now, if you come to the secondary, you remember that is 3.8 faster than primary. That's the reactivity factor. And in that secondary, the chlorine have chances of replacing 4 hydrogen atoms. If you remember, 4 hydrogen atoms, 2 here, 2 here. So 4 hydrogen that are equally chanced multiplied by 3.8 gives us 15. And now, when you now want to know how do we rate them over the percentage? Of course, you remember that now we are saying primary is 6.0, secondary is 15. So when you add the two together, the total will be 21. So what will now be the ratio of the primary? And what will now be the total of percentage yield of primary, which is experimental? It will now be the ratio of primary over total ratio times the total number of percentage we want to share for them. So of course, this one will be 6, total ratio will be 6 plus 15, which is 21. So the percentage for the primary will now be ratio of primary, which is 6, over total ratio, which is 21 times 100 over 1. And that's why you have experimentally determined yield of 2 chloroproduct being 29%. And if you do that same for the for 1 chloroproduct, sorry, being 29%. If you do that for 2 chloroproduct, the ratio of 2 chloroproduct is 15. The total ratio is 21. So 15 over 21 times 100 over 1, that gives you 71%. So that's how we explain the experimentally determined yield for monochloro and dichloro product. We take into consideration the experimentally determined reactivity factor. So 3, which is tertiary, is 5 times faster than primary. Secondary is 3.8 times faster than primary, and primary is just 1 degree in itself. So we can use this to explain why we have those things in every area. So this is another example you can use the same thing that we have justified to look at. If you are trying to do the chlorination or the halogenation of this compound, when you look at it, we have methyl group here. Methyl, 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 methyl. There are 4 of them. So you will be able to look at what is the chances of chlorination of the methyl. And you, of course, when you look at those methyl, there are some methyl that are primary methyl, there are some methyl that are tertiary, there are some methyl that are secondary. When you look at it very well, you discover that methyl here is a tertiary methyl group. It's linked to a carbon, which is linked to 3 other carbons. This one is a tertiary, no, it's a secondary methyl group because it's linked to a carbon that is linked to 2 other carbons. So this is secondary methyl. This is tertiary methyl. If you look at this kind of methyl, it's linked to just only 1 carbon. It's a primary methyl. If you look at this methyl group down there, it's linked to a carbon that's linked to 3 other. So this is tertiary methyl. So when you look at 2,2,5 trimethyl hexane, 1, 2, 3, 4, 5, 6, and you have 2,2,5 trimethyl hexane. If you look at them, okay, there's still 1 methyl group here. This methyl group is primary. And after that, you have methyl group. After that, you have methylene, CH2. This CH2 here is a secondary. This CH2 here is a secondary. That is the second set of proton that can be replaced, or hydrogen that can be replaced by halogen. The third set that can be replaced is a tertiary, is this one. It's a tertiary methine group. Methine group has 1 carbon, methylene group has 2 carbons, methyl group has 3 carbons. So when you look at that, you have different chances. So when you are talking about if the hydrogen that is to be replacing with chlorine is from this side, then you know there are 3, there are about, how many chances? There are about 6 chances of that. And when you look at that, you discover that you have tertiary, you have tertiary. And when you look at that, you know how many hydrogen have equal tendency of getting themselves fixed up. If that is the case, then you look at that and multiply it with the ratio, because you are talking about the primary group is times 1. The secondary group is times 3.8, because it's 3.8 faster. That's the explanation for that one. But if you are trying to look at all of them holistically, then you should be able to know that there will be 3 different U based on where the chlorination will be. It can come on the methyl group, it can come on the methylene group, and it can come on the methine group. So when it comes on the methyl group, we know that there are 6 hydrogen in the methyl group that are primary, and therefore when that happens, it can either be this or this. And then since it's a primary free radical that will be produced there, it will be multiplied by 1. 6 of them multiplied by 1. However, if it is the methine group that we are talking, the methine group means that this place is the one that is trying to replace. If this is the one that is trying to replace, is only 1 of them, and the reactivity for that carbon being a tertiary will be 5.0. So if you use that 1 hydrogen chance multiplied by the reactivity factor, it gives you this. And when we are trying to look for the methylene, which is CH2, there are 2 chances of that. And then when you have the 2 chances of that, you have it here. And then you say, if it's a secondary, what kind of propyl radical, what kind of radical will this be? If we are looking at it as primary or secondary or tertiary, of course, that will be secondary. And if this is secondary, there are 2 hydrogen chances. Then you say 2 multiplied by 3.8, and that gives you that. So this kind of things, you can use it to calculate and predict a lot of things. If you watch that video, it's well explained there too. So these are the degree that helps us to know what will be the reactivity factor we have to use. For tertiary, it's faster, more stable than the secondary. So it will be 5 times faster than primary. Secondary will be 3.8 faster than primary. So anytime you establish that the hydrogen you want to talk about at a particular point in time is a secondary, then that will be number of that hydrogen chances multiplied by 3.8. If it is a tertiary one, number of hydrogen that multiplied by 5.0. That we go when we're talking about the chlorine. But however, if you come to a higher and a heavier atom of group 7, which is bromine, then you look at some other things. The relative rate of radical formation by bromine will be temperature dependent. So, and at 125 degrees centigrade, of course, you know that reaction of bromine cannot be as fast as that of chlorine. When chlorine will go on its own naturally to react, the bromine will need thermal energy to help it. Therefore, at 120 degrees centigrade, you can see that the tertiary will be 1,600 better than the secondary. Secondary will be 82 better than the primary. So the rate of increase in formation, if you are using bromine instead of chlorine, is what we are in here. So you can use that to look at disparity and any other thing you want to look at. These are all what was used here. Remember that bromine is used in this second set. So you are going to be using that 1,682 and 1. But up here you have the chlorine. So you are going to be using the ratio 1 to 3.8 to 5. 1 to 3.8 to 5. But for bromine, you will use 1 to 82 to 1,600, but at a higher thermal condition. That's why you have the heat of formation here, giving you that you have carried the bromination out at a higher temperature. So that's activity. When 2-methylpropane is monochlorinated in the presence of light at room temperature. 36% of the product is 2-chloro-2-methylpropane, and 64% is 1-chloro-2-methylpropane. From this data, calculate how much easier it is to abstract an hydrogen atom from a tertiary carbon than from a primary carbon under this condition. So here I know there will not be problem for us to solve that. The first thing is to establish your the formula you want to relate with, so that you're able to identify each of your compounds. If you say 2-methylpropane, propane has 3 carbon. So if you say 2-methyl, it means on position 2, there's a CH3. If it is 2-methylpropane, propane means carbon is tetravalent in nature. So this carbon already have 1 bond here. You need 3 more to make 4. This middle carbon already has 1 here, 1 here, 1 here. So you need only 1 more. So I can put it by the side, or I can put it on top. And this carbon has only 1 yet. So we need 3 more. So I can put the 3 hydrogen here. So when you look at this now, we'll discover that if you are to chlorinate it in this position, it means that nitrogen will go away from here. So you have a methyl radical that is willing to abstract a chloro radical. So if you have this, this is a primary radical. The same thing if it comes here, it's a primary radical. And if it comes here, it's a primary radical. However, if it is this second one that is to be chlorinated, you discover that it is the only carbon that is a tertiary radical. If you clean up, so this one has 9 chances. So you look at this one. Let's look at the other one. So if you have this one still being 3, and all of that in 3, and this one is the one that you want to remove the hydrogen from. If you remove this hydrogen away from here, this one will become a tertiary radical. And that's telling us that you have to combine 2 things. Reactivity and probability must be combined in order for you to get the accurate figure. So you use that to prove it and then establish what you have. Monochlorinated means it's only 1 chlorine that wants to come in. So that chlorine have 9 chances of being on the primary radical, and it has 1 chance of being on the tertiary radical. However, you remember that the tertiary radical is 5 points faster and better than the primary. The second is 3.8 better than the primary. So you have to count the total number of chances and multiply it by that reactivity factor in order to get established what is to be done here. So I want everyone to try this for the next class. If you have any challenge there, then you can ask. But of course, I believe you don't have any challenge there, because I've already asked before we start today's meeting that if there's any question concerning the video you watch and nobody has that question. So it means I know that you already understood how all these things were calculated and how you can use it to predict. So you try also to explain why chlorination or bromation of methylcyclohexane will produce a greater yield of 1-methylcyclohexane. Can somebody help us with that? Can anybody assist? So what we are saying is that in this number 2, we want to explain chlorination or bromation of methylcyclohexane. This is cyclohexane. This is cyclohexane. Of course, each of those carbon has 2 hydrogen for it to be tetravalently completed. But they now say 1-methylcyclo. It means on position 1, there's a methyl group. This is 1-methylcyclo. If I have to put all other ones, it means the next to this with hydrogen. This carbon already have 2, so it needs 2 more. There are 2 hydrogen. This carbon already have one up, one down, so you need two more. There's a hydrogen, there's an hydrogen. So you see methylene group, plenty of them. This one has one hydrogen, another hydrogen to form 4 bonds. This one already have one up, one down, so you need 2 hydrogen. This one have one up, one down, so you need 2 hydrogen. So the exact number of hydrogen in all of the carbon of one methyl cyclohexane is what you have here. They now said, okay, if you chlorinate this thing, one chlorine is coming in. There's tendency that one chlorine can replace any of the two hydrogen around each of this carbon. That's one chance. Or you can replace one out of the 3 hydrogen of this primary methyl group. That's another chance. Or you can replace the only one hydrogen on this tertiary carbon. That's the third chance. So if you say one allo, one methyl hexane, it means what is replaced is this hydrogen. So one methyl is still methyl, then this is the halogen. So one on carbon 1, there's a methyl. On carbon 1, there's a chlorine. We call it allo here because it can either be chlorine or bromine. If you are using chlorine to your explanation, it will be 1 chloro, 1 methyl cyclohexane. If you are using bromine for your own, it will be 1 bromo, 1 methyl cyclohexane. So explain why chlorination or bromination of cyclo will produce a greater yield of this. If you look at it carefully, if the halogenation has to come on this, it must have been a primary radical. For an hydrogen to live here, it will be CH2 with a dot. That will be primary radical. If it's to come to any of these CH2, 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 you can see if one of it leave to become a radical, then it will be a secondary radical. But if it is this carbon now that is having this hydrogen leaving to become a radical, is linked to a carbon here, linked to a carbon here, linked to a carbon here. So this carbon 1 is the only tertiary radical that can be formed if chlorination must come on top of him. So you have 1, 2, 3, 4, 5. You have 5 secondary radicals that can be formed. You have 1 primary radical that can be formed, and you have 3 primary radicals that can be formed based on the 3 hydrogen on 1. So this is a primary. This is the only tertiary, and you remember tertiary is faster than secondary. Secondary is faster than primary. So if you know that, then why is the product forming chlorine on carbon 1? Why are we forming a larger portion of 1 chloro, 1 methyl cyclohexane instead of having the chlorine around this place or the chlorine on the CH3? Can somebody attempt? You know, when you see 1 chloro product, it's possible that you can have your primary. You can have your primary. CH3 here is primary. It can be the one that will take down 1 chlorine. All you need to do is that 1 hydrogen is gone from him to form a radical, and now use that now to form chlorinator. This is a product that is possible. It is also possible that each of your methylene group, may be the one that will now do the chlorination. Because of course, any carbon that have hydrogen have tendency to lose its hydrogen for chlorine to come in. This is the second chance. So either any of the chlorine on this 5 group can be. That's the second chance. And the third chance is this, wherein it will be the CH3 is here, and your chlorine will be here. So you have 3 tendencies for monochlorination of this compound. But they are saying out of all these 3 tendencies, it was discovered that the one that had the greatest yield is the one in which chlorine came on this carbon number 1 of cyclohexane. Why? Explain. Okay, so I've tried what I can do. If no comments, then we continue from there next time.
So there's something in my mind. I don't know if it's true.
Yes, I'm hearing you.
Yes, I think because why we have more yield is because the chlorine is actually attached to the tertiary hydrocarbon.
Yes, it's attached to tertiary hydrocarbon. I've already mentioned that. Do you know how to calculate it using your probability and reactivity factor?
Yeah, I think we can try that too.
So if you are able to try that and calculate it, it will give you exactly the highest yield. That's when you can use experimental explanation to say that truly the tertiary carbon radical will be a more productive one, because it will take into consideration both the probability factor and the reactivity factor to selectively say that yes, the tertiary is more prone to it. So it's by explanation, you can say that, but by calculation, you should be able to establish that the factor of the tertiary will need 5.0 times the reactivity and some other things put up together, just the same way we did that 29% and 71%. Now, if it is bromine you want to use, then you must consider the temperature. The temperature, you must be able to state that the temperature must be around 125. Then apart from that, the factor for the tertiary in the bromination will be 1,600 faster than the primary, and then the one of the secondary will be 82 faster than the primary. So the primary here we have the lowest yield, the tertiary will have the highest yield. So if you are to predict it using that calculation will give you percentage of each one of them. You say, yes, truly I've seen now that the one halo or one chloro, one methylhexane, cyclohexane has the highest yield. So I want to, by this, we have come to the end of the class today. I want to thank every one of us for being here. And by God's grace, I will send a video for the next week, before next week, so that you can watch them ahead of time. And if you have any question or anything you want us to look at, you can bring it on board next week concerning that. Oguta, you raised your hand. Do you want to ask a question or say something?
No, sir. That was earlier.
Okay, that was earlier. Okay, yes, just otherwise. So thank you very much, and have a wonderful night rest. So next week we are going to the week 5. We have 8 weeks for this facilitation. Thank you for your cooperation and then for making the class peaceful. And then thank you for contributing also to make the class lively. So it's on this note we are drawing curtain for today's class, and I'll be seeing you next week Tuesday by God's grace, the same time, the same link. Thank you, and stay blessed.
All right.